Okay, so this is a short video about experiment number 4, which is called the reactance, impedance, and phasors. I've opened up Circuit Maker, as you can see here, and the circuit we're going to deal with is a 1.5 k ohm resistor and a 0.1 microfarad capacitor set up as shown. And what we want to do is deal with the idea of capacitive reactance and how resistance coupled with capacitive reactance gives us an impedance, and the fact that the reactance of the capacitor is a function of frequency. So let me run this. And when I run it, it turns out that I see an oscilloscope screen over to the right and a Bode plot screen. By the way, you should notice that the banner over the oscilloscope is a little bit darker than the banner over the Bode plot. So the oscilloscope is what's active right now. If I was to go over here and change, what I'd do is I'd get a different input. I go back here, I change, I see a different output. It shifts a little bit horizontally on the screen here. Nothing changed over here. If I click on the banner, it turns out now the Bode plot is the one that's active. Now, I'm going to blow up the Bode plot. And Bode plot is synonymous for network analyzer, circuit frequency response. Bode was a guy that's, this was named after. He was the first one to show it. And what it is the output of the circuit versus the input frequency. Another term for this is the circuit transfer function. What transfers to the output from the input? So if we take a look now, we see we start here at 1 hertz on the far left, we go all the way to 1 megahertz. That's a huge amount of frequency, a factor of 1,000,000. On this scale, it's 500 kilohertz in the center. What we normally do is we take and change the x-axis to a log axis. You hit OK, and now you notice that for equal increments here, I go from 1 to 10, 10 to 100, 100 to 1K, 1K to 10K, to 100K to 1 meg. Again, 1, 2, 3, 4, 5, 6 decades in frequency. And we could extend that. I could go as far as I want over on the right-hand side there, up to gigahertz, 100 gigahertz, terahertz, whatever. And that allows us to show what's going on with the circuit over a wide frequency range. Now, it's pretty obvious what happens here, that at low frequencies, all the way up close to 1 kilohertz, most of the time, whatever we put in comes out of the circuit. It kind of tails off to about 80% at 1 kilohertz. And then we have a kind of a sweeping downward trend where it's difficult to say actually how much comes out at 100 kilohertz and 1 megahertz. Let's go back to the circuit, drag this down here. And why would that be? Well, you might want to recall that what happens is a capacitor has reactance, and reactance is given by the equation of 1 over 2 pi fc. So when f goes towards 0, reactance heads towards infinity. And if we take a look at this circuit, it's a series circuit, and if the capacitor is infinity in size as far as reactance, the vast majority of the signal would appear across here. Matter of fact, if we take a look at this another way, we could say it's like an open circuit, and whatever we put in comes out. On the other hand, if I go to high frequency where f approaches infinity, what happens is the reactance tends to go towards 0. And now what happens is everything would drop across this resistor and hardly anything here. This eventually becomes a short circuit. So what we see is the output going very low at high frequencies. We're still not done with this chart over here, though. This is not the preferred way that engineers, electrical engineers in particular, like to show this. I'm going to do one more thing. I'm going to go here, and I'm going to go and change the y-axis to decibels. I'm going to hit OK, and now what happens is we have even a better representation. And dBs are ratios, by the way. Over on the left-hand side of this, again, all the way up to about 1 kilohertz, whatever we put in seems to come out. And we have this nice linear slope downward that shows us the frequency response. We call it the roll-off rate of the filter, or the circuit in this case, which is actually a low-pass filter. Decibels, again, are ratios, and over here, -10, -20, -30. Each time we're going down by a factor of 10, we're going down by a factor of 10 times. So here, the output is this. It's 10 times smaller here, 100 times smaller here, 1,000 times smaller, 10,000 times smaller, and so forth. And we have cursors again, as we had before for the oscilloscope, where we can take and move around. Here's a cursor B, which is frequency. And behind my head over here was cursors C and D, which I can move up and down. And these are in decibels. So it turns out that the Bode plotter here gives us the kind of frequency response, transfer function, whatever you want to call it, of a circuit. Oh, one other thing, let's go back to here. It turns out that I can show phase in degrees. So if I click on this guy, what happens is it shows me what the phase angle of the circuit is as I take and put these cursors out of the way, as I take and go from a low frequency to a high frequency. You might notice that I go across about 45 degrees here at, let's see, this is about, let's see, 45.33 at a frequency of about 1.3 kilohertz. So the phase angle goes from a low angle of phase to basically 90 degrees. And that is caused by the reactance of the capacitor. At low frequencies, the effect of the capacitor is minimal. There's hardly any phase shift. At high frequencies, the capacitor predominates, and it turns out there's a large phase shift. That is the phase shift between the input and output of the circuit. So I'm going to go back and put this on. Let's see. We'll put it on decibels again, and here's our circuit. So again, I can take and look at, if I want to see what's going on at 1 kilohertz, I can see that, and I might have to blow this up. D is at -2 dB at 1 kilohertz. If I want to have numbers, I can take and again go back here and change this to magnitude, Y to magnitude, and hit OK. And it shows that I'm down to about 0.8 of the input at the output at 1 kilohertz. And again, I can go and fill in. Here's 2 kilohertz. If I drag down this cursor here, I can take and put it at the center, and I get, about 0.544 of the input makes it to the output. Okay, so that's about it for this particular video.